Hey everyone, welcome back to another pre-calc lesson. I'm sitting here with my dog on my lap trying to teach this lesson. She's asleep, so if you hear any weird noise in the background, it might be her collar or who knows. She's old. Okay. So, title of today's lesson is 7.1 Special Triangle Review. It's called Review because it is a geometry lesson. But moving into the next thing we're going into, you have to have this knowledge. So I'm taking a day to go over it. So in geometry, there's two triangles that are considered special. You should recall one is the 45-45-90 triangle. That's one that has two 45-degree angles and, of course, a right angle. The other is the 30-60-90 triangle, which you can see here has 30, 60, and 90. I'm going to talk a little bit about each one and then show you what you're going to be expected to do with your assignment. Okay, with a 45-45-90 triangle, there was a theorem back in geometry that basically said if two angles in a triangle are equal to each other, then the sides opposite those angles would have to be equal to each other as well. And if you recall, that's called an isosceles triangle. So as long as those two angles equal to each other, then these two sides equal each other. And that's the way it is in a 45-45-90 triangle. Oops. Now, since they equal each other, you can call them both the same name. You wouldn't have to call them A and B, and then, of course, the hypotenuse C, A, B, C. You can call them both X, or both A, or both B, or whatever you want to. But what we can do with these special triangles is, instead of making all three sides different variables, you can make all three sides, if not the same variable, at least related to the same variable. So like the third side here is not going to be X. It's clearly longer than the other two, so it can't be X. X would mean they're equal. It's not equal, it's longer. But we can still write that side in terms of X. Now what does that mean? Well, temporarily, I'm going to call this side, well, let's just call it C. Hypotenuse is normally called C, okay. And we can do the Pythagorean theorem. But instead of a squared plus b squared equals c squared, I'm going to write it as x squared plus x squared equals c squared. Forgot that square. Okay, because a and b are both called x. Now, x squared plus x squared, that's like terms. You can combine that, and that's 2x squared equals c squared. Now, if we want to solve for c, that's the goal. What does c equal? All I have to do is square root both sides. The square and the square root cancel out. I get c equals. On the other side, I have square root of 2, square root of x squared. And this square root and that square cancel out, leaving us radical 2x equals c. So this hypotenuse, instead of calling it c, I'm not even going to call it c equals. I'm going to call it radical 2x. And so now this is a pattern that all 45-45-90 triangles fit. What does that mean? Well, if I give you a 45-45-90 triangle, so I'm telling you this is 45, this is 45, this of course is 90, and I say this side is 7, how big are the other two sides? You don't have to do trig to do this. I mean, you could do tangent and sine and whatever to find the other two sides, but you don't have to. You know that this side is going to be 7 because these are equal, and then because of the pattern that's developed up there, this side is radical 2 times 7, which normally is written 7 radical 2. Actually, you put the radical after the whole number. So I'm going to rewrite this instead of radical 2x, x radical 2. But anyway, so x radical 2 is sort of the pattern for all 45-45-90 triangles. If I told you that this side was 19 radical 2, then you would automatically know that these two sides are both 19. Just because it's the pattern, it always works that way. So that's what's special about the 45-45-90. Hopefully you remember kind of doing a lesson like this in geometry. The 30-60-90 triangle is the other special triangle, and in order to understand it, what you actually have to look at is at first an equilateral triangle. An equilateral triangle is a triangle with 3 equal sides. So my drawing down here, when you look at the dotted line and throw that in, it's supposed to be an equilateral triangle. So all three sides are the same, x, x, x. When all three sides are the same, that means all three angles are the same. And since in a triangle, all the angles add up to 180, that means all angles have to be 60. So an equilateral triangle is also what we call equiangular, meaning all three angles are the same. They're 60, 60, 60. A 30, 60, 90 triangle basically comes from this equilateral or equiangular triangle and then cutting it in half with a right angle, a perpendicular bisector as it's called. And then the half you get now is 30, 60, 90. But if we cut it in half, this side isn't an x anymore, it's 1/2 x, which takes me to this diagram here, because it's going to be a little neater than that diagram up there. Let me switch colors to that dark blue. So, okay, if this side is x, this side down here is 1/2 x. Does that make sense? You could also call it x over 2. X over 2 and 1/2 x are the same thing. The question is, what is the remaining side over here? Now that's a leg, right? X is the hypotenuse if you look at this right triangle right here. So if we want to find a leg, I'm going to go ahead and call it A, just for now. So we have A, B, and C, if you want to use those terms, A, B, and C. We're not going to use those terms. We're going to use X. So I'm not going to worry about B and C at all. We already have X and 1/2 x. A, I'm going to use as a variable temporarily. But kind of like what I did over here, I want that side to be in terms of x, so that we just have one variable for the whole triangle. So if I do the Pythagorean theorem, I'm going to have a squared plus the other leg, which would be 1/2 x squared, equals the hypotenuse squared, x squared. Now we want to solve this for a. Well, first, 1/2 x, the quantity squared, would become, okay, 1 squared is still 1, 2 squared is, of course, 4, and then x squared would be x squared equals x squared. To solve for a, now I have to subtract 1/4 x squared on both sides. And that cancels out. I get a squared equals. Now what is x squared minus 1/4 x squared? Let me do this arithmetic over here where I have a little more room. Okay, so x squared does not have a coefficient, but if there's no coefficient, you can assume it's 1, right? Every variable, if there's nothing else, there's a 1 in front of it. And 1 is the same thing as 4/4. I mean, it's the same thing as 2/2 and 3/3 and 4/4 and 5/5, 5/5, etc. But we're going to choose to call it 4/4 because we're subtracting 1/4 from it, and we need this thing called a common denominator, right? So 4/4 minus 1/4 is 3/4, and then keep like terms, x squared. So back to our original equation right here, where we have x squared minus 1/4 x squared, that's going to be 3/4 x squared. Now if I want to isolate a, I need to cancel out that square, which doesn't even look like a 2. Come on. All right, sorry about that. To cancel out that square, of course you need to square root, which means square root the other side. This cancels out, you get a equals, now the square root of 3/4 x squared. That breaks into the square root of 3 over the square root of 4, square root of x squared. This square root applies to the 3, the 4, and the x squared. And a couple of things. Simplify. Well, first of all, you cannot simplify the square root of 3. That's irrational, so we'll just keep that radical 3. The square root of 4, of course, is 2. And then the square root of x squared cancels, and you just get x. So now we have this side, which I was calling a. I'm not going to call it a anymore. I can call it square root of 3 over 2 x. Square root of 3 over 2 x. So let me make this a little simpler. There's this side I'm just going to call 1/2 x. You could call it x over 2 if you wanted to, but there. So now what we have though is a right triangle. It's the special 30, 60, 90. And all three sides can be expressed as x instead of a, b, and c for leg, leg, hypotenuse. What can you do with that? Well, it's kind of like the examples I gave you for this one. Honestly, I don't want to go there right now. Let's wait till we get to the examples. So the first page is all going to be 45, 45, 90 triangles. And then the second page will be the 30, 60, 90. And then that's it. That's the whole worksheet. It's just doing a few problems here. So you're supposed to find the missing side lengths. We have done this in trig. In fact, in trig, we did, air quotes, solve the triangle. Solving the angle isn't even required in this problem, but it would be easy. It's going to be 45 degrees because this side is 45. It has to be. So this is optional. You don't have to write that in, but you might as well. All right, now, this side down here is 7. That's one of the legs, which means the other leg has to be 7. So you don't have to do any calculating at all. You just automatically know that side is going to be 7. And then the hypotenuse, now, could you do the Pythagorean theorem? 7 squared plus 7 squared equals x squared. Yeah, you could. Maybe for kicks I will on this one problem. I really don't want to, if you can tell from my voice, because I already know the answer. But anyway, 7 squared is 49. 7 squared is 49 equals x squared. 49 plus 49, well, 50 plus 50 is 100. So 49 plus 49 is 98. Square root both sides to get x. 98 is not a square number, but you can simplify it into 49 times 2, and 49 is 7 times 7. We've got a pair of 7s there, so this becomes the square root of 7 squared times 2, which is the square root of 7 squared times the square root of 2, and then the square root and the square cancel, and you get 7 radical 2. So this side there, I just did the math and said, found the answer, it's 7 radical 2. But again, if you just look at the notes, it's a pattern. It always happens. This side is x square root of 2. And in this problem, the x was a 7. So of course, that was 7 radical 2. If you know the pattern, you don't have to do any of this busy work. Let me look at, well, shoot. Yeah, your number 1 is going to be a lot like number 2. I almost wish I had a couple of these to drive that point home. This side has to equal that side. This side is going to be that side times radical 2. There, I kind of just gave you the answer in a way. All right, number 4. Now, number 4 is going to be a little trickier. So if you notice in the pattern, the hypotenuse is supposed to have a radical 2 next to it. And this 9 does not have a radical 2 next to it. So what the heck is up with that? Well, that actually brings us to a slightly alternative version of the 45, 45, 90 triangle. So let me add this to your notes. So here, right angle, 45, 45 degrees. So the normal pattern is x, x, x radical 2. What you can do, if there's no radical 2 in the given problem, is you can take the original diagram and divide all three sides. I said 3 and I wrote the word 3. Divide all 3 sides by radical 2. This cancels out and gives you just x. So then we get a new pattern, which is mathematically equivalent to the old pattern. Let me erase those 7s. They were just for that one example. So this new pattern is equivalent to the old pattern. X over radical 2 here. X over radical 2 here. Of course, these two have to equal each other, and just x there. So there's a way to make it so the hypotenuse does not have a radical. The one problem with this, you're not allowed to have the radical in the bottom of a fraction. That's a thing. So I don't know if you remember how to rationalize, but you multiply by radical 2 over radical 2. And so this gives you square root of 2x over square root of 4, right? 2 times 2 is 4. And of course, the square root of 4 is 2. So you get radical 2x over 2. And man, that looks like a mess. But here's what it boils down to. This side can be called radical 2x over 2 instead of x over radical 2, because again, there's that rule where you're not allowed to have roots in the bottoms of fractions. So then you change this to that, And then, okay, normally you put the number in front of the radical. And there, finally, we get the final form of this. So the original fairly standard 45, 45, 90 triangle form or pattern, I highlighted too much, is right here. This is like the standard. But then there's an alternative for when there's no radical next to the hypotenuse. And it is, let's see, I want to circle this in highlighter. It's this one. So, oh my gosh, that was a lot of talking. What does that have to do with this problem? Okay, the hypotenuse is 9. There is no radical. That means that this side is going to be 9 radical 2 over 2, and so is this side. 9 radical 2 over 2. So the original pattern didn't really apply to this problem, so you had to have the alternative pattern, which might lead you to ask, is there an alternative pattern for this triangle? And yes, there is, but I don't think we're going to have to worry about that. So let's not. All right, last one. Number 6. So we have 5 radical 2 over 2, and that is a leg. That means the other leg has to be 5 radical 2 over 2. Now, which pattern is this? Well, both legs have radical 2 over 2 in them, so that's going to be the alternative version, which means that the hypotenuse on this problem is just going to be the 5. So there, let me check. I forgot to check my answers. So number 2, we'll scroll down to the answer key and check that first. Looks good. They wrote the answers here instead of up there. Number 4, m and n are both 9 square root of 2 over 2, or 9 radical 2 over 2. Very good. And this one, m is 5, n is 5 square root of 2 over 2. M is 5, n is 5 square root of 2 over 2. So hopefully you recall learning this already, and this has just been a review. If not, if this is fairly new material or brand new, the first time you've ever seen it, boy, I hope I didn't rush through and make it too confusing. So before I finish the paper, let's summarize again. 2 what we call special triangles. One special because it's isosceles, the other one's special because it's half of an equilateral. Also 30 degrees, 60 degrees, 45 degrees. Those angles kind of come up in physics and engineering and all sorts of applications all the time. So they're kind of fundamental angles anyway. But the 45, 45, 90 has a main form and then kind of a secondary form that gets used a lot. The idea is if you learn these forms or you have them in notes, you don't have to do the Pythagorean theorem on every single problem. By the way, I did the Pythagorean theorem on number 2 just to demonstrate it. I could have done it, and so could you, on 4 and 6. So if you go to do your homework and you're lost and you don't know what to do at all, you can do the Pythagorean theorem. It'll eventually work. It's just a lot more work than if you learned the form. So 2 forms for 45, 45, 90, 1 form for 30, 60, 90, which we're about to get to right now. I'm going to be scrolling up and down a little bit. So that's 60 degrees up here, which means this is 30. You don't necessarily have to write that in, but you can. We're given the shorter leg. The shorter leg is across from the smaller angle. The longer leg is across from the bigger angle. And then we have this relationship in the pattern up there that the hypotenuse is always twice as big as the shorter leg. Here, let me go back up and double check. Now this triangle is sort of rotated. The one we're looking at is drawn more like that, but that's okay. So the shorter leg is half as big as the longer leg, right? So, I'm sorry, the shorter leg is half as big as the hypotenuse, not the longer leg, the hypotenuse. So if this is 6, that makes this one 12. Now what about the shorter leg? I'm sorry, I keep saying the wrong thing. 6 was the shorter leg. Now we're finding the longer leg. Good grief. If you learn anything today, consider yourself lucky, because I sure am not doing a good job teaching. Sorry about that. All right, let me go back. The longer leg is the hypotenuse with a square root of 3 over 2 in front of it. The hypotenuse is x. This is square root of 3 over 2x. So to get this leg, I have to take the hypotenuse, 12, and multiply it by square root of 3 over 2. Now, this will actually simplify a little bit. That's 12 square root of 3 over 2, and those cancel, and you get 6, right? 2 goes in 12 6 times, 6 square root of 3. So there we go. Let's look at number 10. So 3 square root of 3 over 2, that is, let's see, this up here would be our 60. This is the longer leg. The pattern says that this side is the hypotenuse times square root of 3 over 2, which means the hypotenuse is 3. And then the shorter leg should be half of the hypotenuse, which you could call 3/2 or 1.5 or 1.5, however you want to say it. So I didn't scroll up or down, but let me scroll back up to this pattern. Again, the short leg is half as big as the hypotenuse. So this side is half that side. This is square root of 3 over 2 times the hypotenuse. Where am I? Right here. This was given as 3 square root of 3 over 2, which you interpret as square root of 3 over 2 times 3. So that's why this 3 goes here, and then half of this goes here. All right, that's a lot of writing. Let me erase some of this highlighting and just kind of leave our answer like that. Maybe I should be checking these. Well, I only got one more, so we'll do this one, then we'll check it. Okay, the hypotenuse here is 2. This side is half as big as that side. Half of 2 is 1. This side is the square root of 3 over 2 times the hypotenuse. When we multiply that, you put this over 1, you get 2 square root of 3 over 2, and the 2's cancel, and this side just works out to be square root of 3. Okay, let's check this. So number 8, x is 12, y is 6 radical 3. Here we go. X is 12, y is 6 radical 3. Number 10, m is 3, n is 3/2. M is 3, n is 3/2. Number 12, x is radical 3 or square root of 3, y is 1. Square root of 3, 1. Okay, once again, you could do the Pythagorean theorem on these if you wanted to, and, well, on these if you wanted to. It'd just take a lot more work to get to the eventual answer. If you're able to just utilize these patterns, you can get to the answer a lot quicker and easier. This whole worksheet might take just a matter of a couple of minutes to do the whole thing, as long as you understand how these patterns work. Okay, I am going to stop there, and now that I've been thinking of it, there is an alternative version of this diagram that is actually used fairly often, but I'm not going to worry too much about that. It's not a big deal, so yeah. All right, I'll stop there. Contact me as usual if you have questions. Otherwise, good luck and have a great rest.